investigate now this function. What I want to do is find the turning points in this function. So you might want to make a note of the function. Let's just investigate this function for a second before we start thinking about finding the turning points associated with it. Compare the function with the wave function that we've looked at before. A in front is the amplitude. Omega is the angular velocity. Phi is the phase. There is a phase associated with this of 0.4. So although we've got a sine function, it's not starting at 0. It's starting here, look. And that's because of that phase. If I wanted to know what the angular velocity was, that's 50 pi. 50 pi. So that means if the frequency is 2 pi, omega equals 2 pi f, that's another formula I know. So if I divide omega, which is 50 pi, by 2 pi, I get the frequency. And that's 25. So I know the frequency is 25 hertz. And so the period must be 1 over 25, which is 0.04. So the time at which it gets to here, it's associated with 0.4. It's 0.4 later than this. So I can work out what the period is, if I wanted to, what that time is rather, because I know the period of the wave. This is the interesting bit though. T, time, that's this along this axis here, so this is a time-dependent function, appears more than once in the function, look. T also appears in the amplitude part of this wave. That's telling me that the amplitude is not constant. The amplitude is given by this function, 4 e to the minus 3t. That's an exponential decaying function. So the amplitude is decaying exponentially, and you can sort of see that here, look. The amplitude is decaying, gradually getting less and less. So if I could put an envelope around this, we'd see it decaying. And if I were to carry on and zoom out on this on autograph, you would see more clearly that this is an exponentially decaying amplitude. So the wave is dying away. So the peak value is dropping off. And the minimum value, so we've got maximum and minimum values, and they're gradually getting less and less and less. I can still do the same thing. I can still find those turning points. I can find what is this maximum. And then if I think about the wave, I can find out, if I've got that point, where is this point? At what period of time is that later? Where is this point? Where is this point? And then once I've got those, I can substitute those values of t back into the original function, this function. Once I've got that t, I can put these t's back in here again and find out the y, the maximum values. And that will be gradually getting less and less. So the idea is still there of finding the turning points. The problem is to find the differential in the first place, because remember step 1, differentiate the function. That's not straightforward because the variable that we're trying to differentiate with respect to, t, appears twice. I've got two separate functions, 1, 2, multiplied together. And that, to me, and those who've done this before, will remind them of something called the product rule, which is a way to differentiate two functions multiplied together. So that's what we're going to have a look at now.